for the bell work quiz what you know you did it, because I have a no name paper for second period. The bell work quiz. Oh yeah. Alright, so A times C method would mean that we need to do 25 times 49. 1,225. No, that's a big number. So for our table, we have to find numbers that will multiply to 1,225 and add to negative 70. These are huge numbers. Anybody come up with that? You got them? Is that all right, 35 times 35. How many people were able to come up with 35? Pretty good. So negative 35 times negative 35 and negative 35 minus 35. So then we'll write it as a 4-term problem. If you couldn't come up with negative 35, just continue right now. And we get 5x minus 7 times 5x minus 7. And then we want to solve it. And we get our answer is a positive 7 over 5. So, did anybody figure out what might be a possible shortcut here? Or what's going on with these numbers? Yeah. Okay, that's really good. That's how you got there. Is that the first thing you did? Any other, anybody notice anything else out there? Any other, anything else special? Actually, there's something special in all 3 problems. What's going on here? Yeah, these are all perfect squares. Okay, so there's shortcuts. When you see a problem with these huge numbers, it's usually a sign, especially like in an Algebra 2 curriculum or the SAT, it's a sign that maybe you should be square rooting. 25 square roots, and so does 49. Okay, so if A and C can both square root, there's a really good chance that your factors are just those square roots. The square root of 25 is 5. And the square root of 49 is 7. Okay, that's called a perfect square trinomial. So I have it written here. Perfect square trinomial. It has its own special name. There's a perfect square in the A spot, and there's a perfect square in the C spot. So to factor it, I actually shortcut it. I don't do this whole process. If I see numbers that can square root, I just write out my two sets of parentheses, and I square root them. It's a 5x and a 7. A 5x and a 7. I keep the side in the middle, and it's done. Super shortcut. Just square root the first and last number. And then we're not having to deal with this 1,225. Now there's a rule, and you kind of use the rule. The middle number has to be like these two numbers doubled. Like 7 times 5 is 35. So in the middle I should have a 70. That's the rule. And that kind of helps you check it. Well, did this actually make sense? Oh, well, 35, 70. Okay. So try the shortcut now in number 2. Did anybody do number 2 the long way yet? The 8 times C method? Okay, good. Now look at the shortcut of it and see if it applies. So I know 9 square roots, and I know 64 square roots, so I'm going to do 2 parentheses. The square root of 9 is 3. The square root of 64 is 8. And I'm factored. That shortcut only works when you can square root A and C, but it's a great shortcut when you realize you can use it. And so there's our x-intercept for solution. Now do a quick check. 8 times 3 is 24. 24 doubled is 48. I know those are the right factors. Number 3. Did you guys write down the homework? I'm going to move away from this screen. Okay, number 3. I don't know the page number, but use this chapter section to find it. 3-2. So when you do the ebook, you do the context anyway. So you go to 3-2, so problems at the back that we've been doing our problem. All right, so this one, we don't call it a perfect square trinomial. It's not a trinomial. There's only 2 terms. This is called a binomial. The name for this is generally, it's called the difference because it's subtraction of 2 perfect squares. So using the A times C method, we would have to put a 0 in the middle. Because this problem is missing B. And maybe you thought it was missing C. That's a little confusing at first, but since it didn't, this is a C because it has an X, does not have an X. What we're missing is the X term. So for A times C, we have to do 36 times negative 25. Did anybody do that? What is it, Kelton? Not bad. Okay, so we need numbers that will multiply to negative 900 and add to 0. Did anybody find them? Kelton. Negative 30 times 30 is negative 900. And negative 30 plus 30 is 0. So we put them in the middle, and then we do the grouping trick. Group these two and take a GCF. Group these two and take a GCF. So these both divide by 5. No, they both divide by 6 and x. 6x minus 5. These both divide by 5. Okay, so using the A times C method, we ended up with 6x plus 5 and 6x minus 5. This is so long, I can't wait to use the shortcut. Is that too small? All right, so instead of doing all that, if you realize what you're looking at is the difference of two perfect squares, you just square root. Notice the square root of 36 is 6. The square root of 25 is 5. And since we need to cancel the middle, since we need the middle to be 0, we do a positive factor and a negative factor. That creates opposites, making the middle cancel out. Bless you. So I hope that we get a chance to look at these shortcuts more. I mean, we will. We use the shortcuts a lot moving forward, but let's look at the little worksheet you did yesterday. I think it was 22 problems, and see if there were any possible shortcuts on there. It was 20? I thought maybe a double number 11 or something. 21. Here's the answers for 1 through 5. Yeah, as I walk around, I also need to see page 195 and 45 to 48. All right, there's 6 through 11. Yeah, number 9 can't be done. Number 9 cannot be done. Number 9 was called prime. Prime means you only can divide by that number or 1. So number 9 could not be factored. So if you sat and looked at that one forever. Questions on 1 through 11? Alright, here's 11 through 16. The problem is if you use a negative, then that 7 would be negative. Did you show me 45 to 49? Like, so not totally beautiful. right, does anybody have any question about this factoring practice? It was a lot of problems. Okay, so you guys grabbing your books, that's good. That's good. We're gonna look at chapter 3-2. Oh, super heavy. Sorry, here's the answers to that 45, 46, 47, and 48. I took everybody. I love your discussions. How do you do this? It's a negative. Let's take a look. So, starting right here in this section, and if you want to go to page 198, you don't have to write all this. I have it written out for you. You're supposed to kind of fill in the blanks. But starting in this section, we begin square rooting negatives. So we've always told you that those aren't real numbers. So this isn't a test question or anything. This is just vocabulary. But we call all numbers complex numbers. And then you have your real numbers that you guys have been working with up until Algebra 2. All of these real numbers. Anything that's not real is called imaginary. And that whole classification there is just the square root of a negative. So up until today, if you were asked to square root -9, you would say either no solution or no real number. Now we're telling you to go ahead and square root it. But you put this little fancy I next to it, and that I means imaginary. And that tells the people reading your math that you actually square rooted a negative to get to that value. I don't really like the fact that we decided to call this imaginary because it seems like unuseful, not applicable. But actually, in the field of electronics, electrical engineers, circuits, all of the people redoing the power lines, all of the science behind that square roots negatives, and it works. Our electricity works, and the math behind it involves square rooting negatives. So we show it with this imaginary I, but the square roots are really the same as you've always square rooted. If it has a negative next to it, you put an I. So if you guys now want to go to page 190, is it? It's not page 199, is it? Oh gosh. So this was page 204? No, I was right. You guys want me to go straight to homework? Is that what you're saying? Okay, I'll do it. I'll do it second period. I owe you guys. So in your textbook, this is page 209. Does it look like this? Does it look like this? Okay, I'm going to do your homework with you, I guess. I'm open. All right, so the square root of negative 36. I don't need to see work for this. The textbook shows lots of different things. I just want to see 6 with a fancy eye. And the fancy eye tells the people looking at my math that it was a negative square root. And if you're confused about that, in the past we would say not a real number, not a real answer, it's still not a real answer, it's an imaginary answer. Yes. So I've just assigned you guys odds. Now, number 3 is more complicated than number 1. Because, do you have a question? No decimals, you guys. I want these in simplest radical form. And that means no decimals. So when I think about 18, I have to think of perfect square factors. 18 is negative 9 times 2. And that's valuable. It's more valuable than 6 times 3. 6 and 3 don't square root. But 9 is a perfect square, so simplify my radical. So now, since I can square root 9, I'm going to. The square root of 9 is 3. Since it was negative, I'm going to put a little I next to it. And that shows the people reading my math that it was a negative. So it's not too different from all of the simplifying of square roots you did in geometry. All right, you guys try number 5, 7. I'll wait a moment. Alright, so square root of negative 16, we write 4 with the imaginary I. 2 times 4i is 8i. You can multiply those. I would never add them because adding and subtracting is complicated. You have to have like terms. But you can multiply just about anything. So I'm going to multiply that. All right, so now number 7. Each one of these is getting more and more complicated, isn't it? Okay, number 7. So I'm going to think about this as negative 4 times. How should we rewrite 32? So it has a perfect square, Brendan? 8 times 4 will work. I'm worried about 8 though, because 8 divides by 4 again. And so that's a sign to me that maybe there's a bigger number I could use. 16 and 2. So you thought of 8 and 4. Now since 8 is also 4, you put those together and get 16. Good job. 16 and 2 will work. Those are the quickest ways. 8 and 4 works, you just have to do it twice. So 32 is the same as 16 times 2. I'm going to cross out this negative 16. I'm going to square root it. It'll be 4i. And so I can now multiply this number that was shown out front and the number that I brought out front to get negative 16i times the square root of 2. Wow, I just did your homework with you. What are you going to do over the weekend to do this? Long weekend? You're not going to have math homework. You guys should do even. All right, what is going on here? Shall we do what the book says and look at example 2? Let's do it. Let's look at example 2. When you see the example, if you make sense of it, so it's page 200. It says we're supposed to actually be finding x and y. And I do. I see x, y, and I see these i's in here. I'm sorry this is blurry. I'm not really. The more I zoom, the blurrier it gets. So this says to set the real parts equal to each other and set the imaginary parts equal to each other. So the 2x and the 10 are considered real because they don't have I. So you can see here, they set the real parts equal. They said 2x is the same as 10. Now, when you guys look at this, can you tell me what x is? The 2x is in the same spot as the 10. So what does x have to be? X is 5. And here they divide by 2 to get x equals 5. So I'm going to do that again here. Negative 7i is the imaginary part. So when I see this, if the left side is equal to the right side, I see that, well, y must really be negative 7. What you do is you take those imaginary parts, set them equal, and solving here, what they did is they divided both sides by y. I mean I. And they get negative 7 equals I. You guys ready to try it in the homework problems? Let's try it. I'm just going to rewrite this so it's not blurry. So we got 4x and I. Those things are considered real. I'm sorry, 4x and 8 are considered real. So this means that x has to be 2. If the 4x is supposed to be the same as the 8, x must be 2. The 2i and the yi are considered the imaginary parts. And the whole purpose of you guys doing this as an exercise is just to start you thinking about these